So that is one of the considerations for his own work, to perhaps look at ways that we can generate while the grains are stored, or by way of modeling heat and mass transfer, we can determine when grains will need drying in these type of silos, then they can be evacuated, dried, and then restored. So the way the silos are designed is such that they can be evacuated gravimetrically. So by weight, they flow out.
How are they loaded?
I think they're loaded from the top, yes.
Do you have data in Nigeria for the wind speed and the amount of wind energy that's available to capture?
Oh yes, sure. There are quite a volume of data. Some of the data, actually, meteorological systems from the airports have wind data, they have temperature data, but they are not always open to the public. But it's accessible. And we hope, that's what I said, that we intend to use historical data for modeling and for design.
So you feel like there is enough wind energy though in the areas there? I mean,
Okay.
you always struggle with that with wind and with solar. You
Yes,
know,
yes.
am I going to have enough energy available to do what I need to do?
Yes. So far from what we've looked at, of the truth, there's more. The north seems to be favorable for everything. There's a lot of wind in the north. There's also a lot of sunlight, and there's also low humidity. Unfortunately, what we have in the south, especially until you get very close to the coastal zone, is you have quite some areas that are laden with rainforest. But if on an average, you still have quite good. Yes, please.
So with regards to that question, the design idea for the wind turbine system is such that it can optimize horsepower generation irrespective of wind velocity. And that's where the idea of variable gas system comes in, to kind of maximize air velocity that is delivered irrespective of the wind velocity that is blowing. So you can actually change, the turning of the fan to increase the velocity of air being blown, if you understand the prevailing wind velocity.
If I do understand, in addition to what you're saying, well, I've looked at that closely because what it means is that you've got to design something that's far bigger than what you expect. Because you're looking at losses, you're looking at the fact that you need to step down if you need to step down, but you can't build up. So you want to build a big system that can run, and then you can optimize if it increases.
Yeah, this seems kind of risky, when you're looking at a real short time frame that you want to get this grain dry quickly. So it stores, and you're really putting a lot of money. You're banking on the fact of wind availability.
Yeah, the good news, yes, I think that's also something. The good news is that in the middle belt down to the south, there's a lot of wind in the rainy season. So, in a way, we anticipate that since we are fighting with rain, we're also getting the benefit of the airflow in that season.
I read the title about mathematical modeling for storage. The mathematical modeling is not about modeling of storage.
No.
It's about mass transfer, heat transfer.
That's what we say.
But
The title says, right?
You have the title, it says mathematical modeling for storage.
So, mathematical modeling of heat and mass transfer in local silos.
You can go up the last slide.
All right, I'll take it.
And also, I think you're focusing on corn in your research. That's what you showed the silage. You better put corn quality, not grain quality, because for wheat is different. Using concrete silage for with this particular diameter, with a particular capacity for width, and we try to keep width for 6-7 years. So it's not the same as corn. So if you're using grain quality, it's covering all grains. So I think it's not correct to use grain quality. For example, when you're talking about millet, the size is different. Your mathematical modeling can be different. So you cannot use grain quality. You better put corn quality because you're focusing on corn quality.
Okay, right. I note that, but like I explained earlier on, first of all, in developing countries, there's an interesting scenario. Most developing countries of the world fall within the tropic region. And if you observe that, it's also likely that certain grains like wheat are not grown in those regions. Now, for the grains that are grown in these areas, they have similar conditions. I agree that the model for corn may not serve for them, but we took corn because corn is the largest farmed product, and we are imagining that if you get something working for corn, you can make adjustments to that model to fit for any other product. And so that's why I still think it's just, but if it's considered like we should change that, I'm open to that.
The other reason I'm saying that because in grain quality, the important important component is the starch. In corn, we have high amount of starch. The starch just affects to absorption of moisture, which you measure in here. But for example, if you consider millet, we have less amount of starch in it. Or wheat is different from corn. So you need to consider that because you're measuring, you're reducing moisture before silage, and you try to use a combination of winding system and also solar system to dry grain before silage. All right. Other question is, in your design, combination of wind system application with solar system application is not clear. How you put these two together to using for, your research?
I think I made the point very clear that we're building a wind system that generates air, and we have a different model that takes over from the air that is generated from the wind system and preheats it before you serve it. And I don't know if whether...
I think that that's a very valid question, because the question is, then why are you trying to introduce forced air into the system?
Okay. No.
Why not just natural convection? Why forced convection? And what is the relationship between the forced air and the solar system that you just showed?
Okay, right.
So how do the two intermingle to enhance the efficiency of drying?
Okay, so
that is, I guess that's his question.
okay, if I didn't understand it, thank you for that. Basically, it is general knowledge that forced convection improves the rate of heat transfer. And so we look at using that for advantage. Secondly, we also mentioned earlier on that if we don't use forced convection and you leave it to natural convection, there is going to be a situation where you're going to have stagnation of moisture-laden air within the system, which is going to recondense within the system and cause more spoilage. So you don't want that. So your interest is to be able to get your moisture out of that zone as fast as possible. And once you can elevate the temperature, then you improve how fast that can happen. So that's basically why we're coupling the two together. And the models are, if you like, separate, but coupled together. It's all about assembling the design.
Good. Any other questions?
We still have time, but did you calculate the solar energy collected from the pebble bed?
Sorry?
Do you calculate the energy that you can get from the pebble bed that will...
The solar collector.
Okay,
Yeah.
right. Okay. Let me say this. At this stage, not yet, but we're going to have to do that. I took it for granted because I've worked on solar energy. I did that on the master's level. When I started teaching in the Polytechnic, I adopted a Skyflower collector for food drying. So it's an area that I'm quite vast with already. So I know that we need to do that to get our figures.
I have a question. You didn't show your inner mass transfer equations. We didn't see that.
Well,
You didn't provide boundary conditions, initial condition, all those things. You didn't show them. So
right.
I mean, you just mentioned them.
No, I do have them, but I was also considering that I have just 20 minutes to present. So I didn't want to put something that's going to take me the whole day here. But we have data, we have fundamental equations for that. And talking about boundary conditions, like I did say, right? So, in fact, when we started, we were looking at heat, moisture, and momentum transfer. But I also realized that there's almost like a standard to evaluate hydrostatic pressure losses within any system. So, since our focus was going to be more on heat, basically moisture, not even heat per se, I needed to work on both heat and mass. So, but we're going to be working with all of that in their various forms, and we are putting them. We're looking at either using Excel, using the MATLAB or using a specialized software. But I think I want to go with the MATLAB system because it opens the black box for you to know what is going on inside.